Hello, welcome. Okay, we're continuing our series now. Tonight we're going to synchronize all the threads that are running across our kernel. We're only going to be running one kernel at a time, I think, for like this whole series. So we'll be synchronizing all threads across the whole GPU all at once. So let's get started. Okay, to do this, we are before we start our AI art, we need a good classification network. So I'm gonna write a neural network based on this data challenge called MNIST, or provided by MNIST. I don't know, either or. I don't know if they created it or if it's the name of their data set, but I'll go ahead and show you some examples of how this challenge works. It's a pretty old one. What they have is thousands and thousands of these letters or these numbers that were written by hand that you can download, and with them, each of the images are annotated. So it's a single digit, 0 to 9. And they have a set number of them that are for training the network, and then they have a set number that are testing. So you take in the training ones, you train your neural network, so that over time, as you run the neural network over and over and change it slightly, it'll be able to recognize everything in the training set. And that's thousands. And then they have the testing ones. And so we'll run it, we'll run our trained neural network just once for each of those digits, and we'll see how many we get right. So there's been a lot of papers written on this. There's it's a really old one. There's a newer one. What do they call a newer one? It's another challenge, but it's like pictures of different objects. So it might be like an elephant or something. And then that was one like Google, Facebook, these big companies were all competing to get the best on. They'd have a competition every year. Even that one's getting pretty old now. There doesn't seem to be a new one yet. I'm guessing the next one will be video or something like that. But yeah, right now there's not really like a huge... That one, oh, that's called ImageNet, I think. So we'll start with this one. It's easier, and we'll build a neural network, and we'll do it in a scalable way, so that when we create the classifier that we'll need for the AI art project, we'll be able to use a lot of the functionality that we've written, including what we're doing today, which is the thread synchronization. Okay, so I found a paper. All I just Googled best MNIST model. This came up, papers with code. I saw this study a little while ago, so we'll use this. But I'm just showing you like how in the future you could find out information like this. So papers with code. Here's one, and here's the one we'll use. An ensemble of simple convolutional neural network models for MNIST digit recognition. So we'll look at this paper and I'll show you the architecture, and then it should make more sense why we have to synchronize our threads. I will also go into more detail about how CUDA works, but first, I need more sleep. So that'll be a different day, hopefully this weekend. Yeah, so but for now, just know that just, you know, a 30,000 foot view, you're running a lot of cores, tons and tons of cores, and on these cores you run one thread per core. It's not hyper threaded, and there's no guarantee like when any core is running at once. You could have 1 million threads and only 1,000 cores, and it'll schedule for itself. Like in that case, so say you have 2 million threads you're running and you have 1,000 cores, That means each core is probably going to get assigned 2,000. Like the average will be 2,000 that are run. And these threads, they'll just run when the heck ever. They'll run in a group of 32. But nowadays, as we found out the other night, these warps, the groups of 32s, they're not even guaranteed to be running in lockstep. So like instruction per instruction, all synchronized together. So it's Wild West. That's why we need the synchronization here. Okay, so I'll just kind of skim through this. I've read this paper. I've read this paper before. Okay, so they have these three networks: M3, M5, and M7. These are what they came to after some experimentation. Part of their, and we'll go over this, but part of, well, actually, first of all, I'll go over the results. That's a good place to start. Results here. Okay, so with these M networks, they were getting their accuracy 99.67 was the worst one. The others were just marginally better. That's a percentage of the test set that it would accurately classify. So this is really good. Something they did for this project was they would take each letter and then they would kind of transform it a little bit. So you see here it says random translation and random rotation applied to the training image. Thought that they skewed it too a little bit, but they just take the image and kind of move it around and train that. We're not going to do that for this project, but we will use their architecture. Yeah, look how good it is. So each epoch is like when you run all of the training set through the neural network, and then you modify the neural network, and now the neural network's better. That's one epoch. So the you can see it kind of looks like a logarithmic curve, but it starts to really flatten out. So they're getting this good at only like well, they go to 150 epochs. They're getting pretty much up there by like 60. Okay. Okay, it looks like they combine the networks together. Probably with voting or something. And now they're getting 99.85. Loady. Okay, here's their common network. So networks based on like previous common architectures. I'm not going over this today, but just know that each of these are layers. Maxpool is super simple. So before cooperative groups came out in CUDA. By the way, I haven't used cooperative groups, but I read about them a while ago, and I was doing CUDA before cooperative groups. And if you want to sync all threads across an entire GPU, then you'd have to, like, given that you're just running one kernel on the GPU at once, you have to run it, and then you have to run your kernel, and then you have to close the kernel, and then you have to go back into like your C++ space, so like your CPU code space, and then you run the kernel again, and now they're synchronized. And they're all default to stream 0 because you can run different kernels. You can launch different kernels like at different times on different streams, and then it can kind of like try to fit the kernels in together across your streaming multiprocessors. Actually, forget about all that. I said I won't go into CUDA too much. I really got to prepare for that and organize the way I explain it all. So you'd end the kernel and then you'd run the next one. So what happens is you get a bunch of functions everywhere, and it just doesn't look very good. It's kind of irritating. You're like read one function and it's not. It can kind of look like it's just like randomly ending. Then you have to go somewhere. Then you have to go back to the CPU code space, see what happens next. Oh, it's another kernel. You have to hop back to it. It's better to just all have it like in line together. So when we'll be running the first layer, and then so the input we'll take in, which will be 28 pixels by 28 pixels. So a total of 28 squared. And then we'll and then we run the first layer, and now we have to wait for all of the results to come in, and before we go to the second layer, because the second layer is dependent on the first layer. So we'll use the cooperative group to sync them together. This is gonna be cool. I wonder how accurate we'll get without like stretching and rotating the images or translating them. Okay, so let's get started. CUDA cooperative. Cooperative groups. So here we go. This is the official explanation of all of CUDA by NVIDIA. docs@nvidia.com, CUDA C programming guide. And so up here it says version 12. You might like be on a forum and click through or something. If you go to an older version, then you can tell by the link. So if you ever get to this page, make sure that you're on the latest one, which won't have any versioning numbers in it. Unless you're using the older version, then of course go to that. What you see on the left here, we've got our table of contents. And as we scroll down, it'll move through all of these. So this entire document explains the entire CUDA programming language, given you already know C++, because this is CUDA C++. I wonder how much shorter the CUDA C is. So on the left, come down, section 8, cooperative groups. Got some changes. I think it came out in CUDA version 9. Cooperative groups, that is. So what we're going to be synchronizing is our grid. So when you run your kernel, it's in one grid. It can have multiple blocks, and then the blocks each have to have the same number of threads running in them. So we want the whole thing synchronized, so we'll use grid synchronization. Oh, they made it 30% faster in CUDA 11. I always love to see that. Okay, so right off the bat, we see that grid group must be constructed with this grid function at declaration time. So when we declare a grid group, when we ever mention it for the first time, we've got to call this function, which means it has to be a local variable. We include cooperative groups, and we don't need to do reduce, inclusive scan, exclusive scan. We don't need that either. So all we need is this. This is really basic, but let's make sure our code still compiles, because I'll tell you a secret about programming. There's just always a lot of problems everywhere. Okay, so we're back here. We're in our main.cu. I'm just gonna test it in the main file, and then when we do mnist, I'm gonna make a new subdirectory for it, starting from the root directory. Okay, AI art narrator. We've got cooperative groups. Let's make sure it finds the header file. There's no red squigglies. That's a good sign. Okay, so we'll use our Windows batch file. Oh yeah, let me check my sound mixer. Oh, I've got the I don't have my main display set correctly. I wonder if I changed. Wait, it does say it is. One is always your laptop screen. I'm looking at I've had my TV hooked up to my laptop. So I'm looking at my TV, which should be 2, because 1 should always be the laptop. Oh, it's just a little bug. Okay, 2. Now let me check my software. Yes, my streaming software. Okay. Build files have been written. Oh yeah, I'm gonna check my volume mixer so that you guys don't hear a bunch of binging and stuff if there's any Visual Studio errors. Visual Studio. Build AI art generator. And it built. Oh, that was in my repos. I should put repos here. Actually, I'll put AI art generator in my quick select or quick access. Okay, build debug, and here it is. Actually, we could just in the code we could just put a pause, so we can just run it. We can just double click the exe to run it. How do you do that in Windows? I think it's system pause. And I don't think you need, I think it is uppercase P. I don't think you need to include the Windows header. Let's find out. Oh, but this is only gonna work in, we might as well keep ourselves strict. And wait, what am I'm doing like CMake syntax. Oopsie daisy. I don't think we need a Windows header. Let's try it. Build. Okay. Success. Debug run. Alrighty. We're only running 128 threads. Okay, so they all ran. Let me see if I can show you guys what happens if we don't. Run all of our if we don't have cooperative groups. I wonder if this will demonstrate it well. But I'll print the thread ID once and then I'll print it again. And we'll see if there's ever an interruption between 1 and 2. Between the first print and the second print statement. First off, let me show you how to tell if your graphics card. My graphics card does support cooperative groups. So let's make sure yours does, and I'll show you how to do that. So we'll go near where there is NVCC. So C program files, NVIDIA GPU Computing Toolkit CUDA, we're on version 12 extras, demo suite. Now here's the applications. In version 12, for some reason, they don't give you the sources. In earlier versions, they give you the sources, and you might have to build it yourself, but it will come with a Visual Studio solution file, so you can just open that up, build it, and you'll have it. And you can run it from Visual Studio. But we just get the straight executable, so I'll open a PowerShell in this directory. So that's hold Shift, right click, open PowerShell window here, and we will run device query. Now this is good information to have, so I'm going to put this in a Google Sheet. I've got some notes and things like that here. I downloaded that PDF earlier of the ensemble paper. Device query.exe. And then let's put this into a monospace font so it's all lined up. Yep. And let's save my eyeballs. So here we go. It's SM March 75. That's how you pass it to the compiler, is 7.5. You pass in a 75, which I showed you guys earlier. We've got 1536 CUDA cores. Okay, well, this is what we came here for. It supports cooperative kernel launch. Multi-device co-op kernel launch. I think that means if you have like 2 GPUs in the same computer, which CUDA supports. But this is a laptop anyways. So it supports, let's look back at this because this is going to be really important for our custom neural network architecture. It's got 1536 CUDA cores, 64 CUDA cores per multiprocessor. NVIDIA also calls them SMP sometimes, streaming multiprocessors, but for some reason it's just calling them multiprocessors here. So we have 24 multiprocessors. 32 warps or threads per warp. And like I showed you last stream, we can only run 1024 threads per multiprocessor. Okay, so we'll build this now with these two print statements. And I gotta pee. Okay. We did that. We already ran the CMake, so now time to build it. We'll just build AI art generator. Still don't know what these are. I'll look that up sometime. Probably off stream. But if we can set CMake to get rid of these, I'll do that on stream. Oh, one failed. Oh, says I can't open it. Oh, that's one thing we'll have to keep in mind with our new pause statement that keeps it from shutting down immediately. All right, built it. You can hit the back button on your mouse if you have back buttons on your mouse to, it works on Windows Explorer too. So the way our program ran was for all of the threads, it ran and printed the first statement, and then second, and then after it was done with that, it printed the second print statement, which doesn't demonstrate that these threads can go like out of order. Like you could have one thread go from start to finish, and then before another thread even starts. But yeah, so we've got to keep in mind what the guarantees are. There's no guarantee it's all going to run the first line and then they'll all the threads will run the second line. So let's use a lot of numbers. Let's do like 1,000,000 threads. 1,000,000. So this is the number of threads per block, and then this is the number of blocks we'll run. And so I'm just putting here that I'm using the modulo operator. If it's divisible by 1,000, then we'll print. But that's gonna be a lot, so that'll be still like 1,000 print. So we'll do 10,000. If the thread ID is divisible by 10,000, then we'll print these. And it's in debug mode, so I don't think it'll optimize it. All right, let's test it out. Yep, see, we have 2's mixed in with 1's. So sometimes the second print statement happened while another thread had not even run the first print statement yet. I don't know why they're all saying their thread ID is 0. Oh, because we're running multiple blocks. And so the thread ID is only the thread ID within that specific block. So to find out, or to like enumerate them, to enumerate your thread number, you can get a block ID, and then you can look up how many threads per block that you have. And we're going to do all on the x-axis. This whole project, we're only going to be on one axis for like thread, or for block and grid dimensions. Okay, so I'll run it, or I'll CMake it again. Make sure to exit it so we can build it. There we go. We have thread IDs, and they're all divisible by 1,000 or 10,000. And that is why we need cooperative groups, ladies and gentlemen. We know our include file works. I don't like using namespace. I like to know where my functions are coming from. And we could abbreviate it. No, I won't. I like that they do recommend an abbreviation. That way, like, if you're looking at someone else's code and modifying it and you don't know what CG is and you Google it, like, this will probably come up if you put in the right words, because they now have a standard abbreviation. Okay, it has to be C++ 11 or higher. That's fine, we're on 17. Like I said, I haven't used this before, but we are synchronizing a grid. In this example, they're getting a description of the block. It's thread block here. And it's all within the kernel. Let's see if the grid, if we have to, if we can simply create the variable within the kernel for a grid. Grid group G equals this grid. Oh, you need to use a cooperative launch API. I guess that much. You wouldn't just make the variable like, or you would make it compatible with grid synchronization within the kernel code, because your grid's running across a bunch of different multiprocessors. So it needs to know ahead of time. Well, probably doesn't need to, but it makes it a lot easier for the compiler developers. Multi-grid group, we don't need that. Yeah, like I said, I don't think we'll use that for the entire project. So we know we're gonna need this within our kernel, so I'll go ahead and put it there. And I think they must be like taking out the namespace by having the using namespace cooperative groups, but we'll have ours in. We are verbose on this channel. So where's this call we do? Oh, it's grid group. Okay, you need to use a cooperative launch API. So let's see. Where that is. So multi-grid needs a launch API. That'd be nice to remember for other projects. Examples, we want our launch API. Coalesce groups. This is interesting since we're here. Coalesce groups. So in CUDA's SymT architecture, SymT is single instruction, multiple threads. So like on your warp of your 32 threads, you have each instruction sent out to them, and apparently they can run out of lockstep now. But you still have multiple threads running with the exact same instructions. So the sequence of instructions has to be the same for all threads within the warp. That's how CUDA works. But sometimes you'll have a thread and you can say, oh, well, if it's an even numbered thread, then do this. And if not, then do nothing. Or do something else. So what happens is like, let's say we had like even number threads. We're adding together an array element and then the element next to it into another array that's half the size. Now the odd numbered threads, those would go to sleep. Whatever's in the if statement. So say you have an if statement, your conditional is it's whether you go and do it or not is dependent on whether one of your threads is a certain number, or if it's a function at all of like the thread number. If it's not running, it goes to sleep. So interestingly, now that we know for Turing, my GPU's architecture, that these threads can run not in lockstep, it appears that if a thread doesn't execute because of a conditional statement, then it goes to sleep still. So it won't continue on past that conditional branch until all the other threads in the warp are done. If there exists a data-dependent conditional branch in the application code such that threads within a warp diverge, then the warp serially executes each branch, disabling threads not yet on that path. The threads that remain active on the path are referred to as coalesced. Cooperative groups have as functionality to discover and create a group containing all coalesced threads. So when you have your coalesced threads running, it's a part of your warp is running and the other part is sleep. It's stuck probably in a spin lock. Then you never want anything within anything the coalesced threads are doing to be dependent on those sleeping threads. Because they'll never unsleep. So this is much better than the old way to do it, which is sync threads, which a sleeping thread won't wake up to call sync threads because it's not in the conditional branch. So that would lead to locking or just like a stalemate. So now you can use functionality like this. So before, basically, you just would never sync threads within the conditional branch that's dependent on the thread number. And now we get this. And we don't need a special kernel call for the coalesced threads. I don't think we'll use this, but it's good to know. This is a CUDA thing to know. CUDA programmers, they make good money. Synchronization. Okay, I'll just go to the grid synchronization. So instead of like our nice looking CUDA syntax that we use to indicate to the NVCC which is the CUDA compiler that we're running a kernel. So these angled brackets, 3 on each side pointing either way. We use CUDA launch cooperative kernel. Oh, that doesn't stand out as much. Oh well. Okay, so we get we create a device property, then we populate it. We put its pointer into this function, and we put the device number. And we've only got one NVIDIA GPU, so our device number is going to be 0. And then we launch it. Our first argument is a function pointer to our kernel, and we cast it to void pointer. So old school. We pass in the number of multiprocessors we have. Then our number of threads, and then our args. So we can put in more than one variable here. They just have to be comma separated like the rest of these. So this number of threads, then, this isn't threads per block. This is total number of threads. Interesting. So could we put in like 7? I wonder if they prefer you make it a power of 2 to run it across multiple MPs. Oh, you get like a... They have this function here, CUDA occupancy max active blocks per multiprocessor, and then you put in your kernel function. Oh, they didn't even, your function pointer, they didn't even cast it to void pointer. How many threads you would be running? A pointer to an integer. And it'll give you back like your optimized number of blocks you should be running per SM. Which you can then multiply by your multiprocessor count. Wow, that's really cool. So basically, you don't have to pick like how many threads you launch per kernel. I mean, you don't have to pick like threads per block, because sometimes it's better to use 128 threads per block, sometimes 256. I'll go into the reasons why for that. Well, it has to do with like your cache sizes and like your super fast memory that's on your MPs. And sometimes I think it's usually just 128 or 256. So that might change too, because now we only get 64 cores per SM versus or MP when it used to be 128. So it'll calculate that for you. And I'm sure you only have to do this once in the beginning then. So it's not gonna like affect our training speeds. That's really cool. Since this is an open source project, we'll be nice and we'll give them a warning if the user's GPU does not support cooperative thread groups. All right, so here we go. Dev number. Let's comment this out, or let's add comments. I'm a verbose type of guy, so we'll rename our variable to something readable, something easily understandable. Supports co-op launch. That's close enough. So say if supports co-op launch. Or we'll say if not. So if it doesn't support a co-op launch, we will politely say this GPU does not support cooperative groups. And then we will return from main with a error code. So this must be a CUDA keyword maybe. We haven't defined it, so let's see if it builds. See, these light up green, I think because they come from NVIDIA, and this one's not lighting up green. So that gives me a little pause. NVIDIA is the green team. All right, here we go. It listed our executable here. Check it out, debug, and run. Oh, we should probably put in a statement if it does. If it does support cooperative groups. Now, this here, I used to do my if statements like this, where you put the we put the curly brace on the next line, but I realized like especially I'm coding in 1080p now. I usually code in 4K because I'm like fancy like that. But this is so short. Like there's I want to make it compact and help other people that have monitors that they need to upgrade after they learn all this shit and get a good job. But for functions, I will go to the next line. This is actually standard Linux. I've been learning Linux lately in Linux driver development. So this is a style recommendation for Linux. That's another reason I'm doing it. This GPU supports cooperative groups. Congratulations! No periods. We don't need to be that formal. Actually, I'm not going to test this. Yeah, I will. Testing. Oh, my screen's broke. I mean, my capture's broke. My video self-capture's broke. I got this new capture card. It's more expensive and it gets kind of choppy. Now it's frozen. I tell you. Plug it in my old capture card. Old one's working. Yep, still working. It's hard to tell sometimes. I can hold really still. I'm a hunter. I'll fix this later. I'll check for driver updates. If that doesn't fix the capture card, I'll return it. It's Amazon. I can just take it to Whole Foods these days to return it. Okay, run this program. We build that was already built. Yeah, it's nice to see your date modified on your executables. Okay, it says it's up to date. Control home. Oh, that didn't work. Control home closes your command prompt. I didn't know that. I was hoping it'd take me to the top. This GPU supports cooperative groups. Sweet. All right, now we're gonna call our kernel with that API call. So we already have our device number. We do need our device properties. Boom, boom, boom. Device. Do device number. You know, I'm gonna put this in my own style. I like snake. Snake spelling. Snake capitalization. They're just general variables. I do that typically. This is a CUDA API, CUDA keyword, but press F12 to go to it. Oh, I guess it's not really like a keyword. It's just part of an enum. That's why it's not popping up green, like cooperative groups is. Device prop. I think props, most people know that means properties. It's not like just something used in sketch comedy. Put in our kernel name, so our kernel function pointer. Okay, so first we'll check if it's compatible with cooperative groups. So we won't be running this. It'll launch from here. We have no args, so I think we can just get rid of that then. No. Oh, maybe it's just squiggly because of that. Oh, it looks like we do need something for args, so... Unless this squiggly shouldn't be here. Func. Oh, this number of threads has to be defined differently. Our arguments are double pointers. Pointer to a pointer. That's weird. That's not how like printf does it. It uses like that VA start, VA end. So that'll be interesting to see how we do this. How we put in more than one argument, or even one argument, because it needs a void double pointer. And then it does end with the amount of shared mem you're using, and then your stream number for your CUDA launch cooperative kernel function. And the last two arguments are optional. So I think grid size and dim size are both structs with 3 values, 3-dimensional. So we'll say our the dimension of our block is 1024 on the x-axis, 1 in the y, 1 in the z-axis. And our dim grid is 1000. Let me make sure it's dim grid. Yeah, dimensions grid. We still have our red squiggly. I think we need to figure out how this how these args things work. How we put in that variable that describes all the arguments that get passed to the function, to the kernel function. Oh, we just make a void pointer. We can just make a void pointer array, and then initialize it. Why is this red? That should be valid. Oh, empty initializer. We'll say, wait, it's the size of 1. And it has a 0 in it. Wait, no, it's the size of 0, right? Oh, yeah, that doesn't make sense. We don't have any arguments. Should we just give it a fake argument? No, I really want to do that. We'll Google this. First, let's grab this CUDA launch cooperative. No, not that one. CUDA launch cooperative kernel name, and then we'll just type in 0 arguments. Okay, here's something. For what it's worth, you can pass arbitrary structs by just passing it via void pointer arguments. Okay, this guy's just asking like how to not build like an ugly struct. This guy's using templating with the multiple arguments. That's not a question. This is interesting though. Like I do want to know how to not have ugly structs everywhere every time I want to run a kernel. But back to the question. We'll look at that later. Oh, how about we'll bookmark this. Bookmark in programming. Okay. Collect argument addresses fails. I mean, we can't just use like an undefined pointer, because it'll get initialized with a value. Like it'll have a value. We don't know what it is. We'll do no arguments. Medium's got a lot of good stuff. Okay, cooperative groups require kernel launch to be changed. The kernel should be launched with CUDA launch cooperative kernel in order to use grid-wide barriers. You know this? See, he's got... Or this isn't a struct, but it's like an ugly... It's an ugly array of pointers. But we don't have any arguments. Should we just, for now? No. We'll get through this. How come no one's asked this question? Actually, we'll refer back to the official documentation and see. Maybe at the end it had no. No, it doesn't talk about it. Oh, you know what? Maybe these red squigglies are wrong. We'll just not have it there. Well, it doesn't have an overloaded function though. Let's see. There's 4 references, they're all right here. There's no overload without this here. Oh, here's a little bit of notation. Of notes. If the kernel has n parameters, the p, is this something for like formatting or like some interpreter? The arg should point to array of n pointers. Each pointer from 0 to the last one point to the region of memory from which the actual parameter will be copied. Doesn't say what to do if there's no arguments. Yeah, you know what, we'll have arguments always, so we'll just pass in a fake argument. Okay, unused param. Okay, yeah, make sure our variable names match here. Okay, so we're gonna make an integer unused param. And we'll cast it to a void pointer. Oh, we've got to get its address first. And now we can pass in our kernel arguments. So this is an array of void pointers, is what we're passing in. Still got the red squigglies. Oh yeah, so that backslash P isn't showing up anymore, so this must be like some type of formatting send that VS Code can interpret, probably other things like Doxygen, other like comment reading tools. Okay, so we want a void pointer for the kernel. Oh yeah, this is my kernel. Integer for multiprocessor count. Yep, 2 dim3s, then an int. Oh, because we want. Wait, no, we don't want. We want to pass in the whole array. Yeah, we're not getting the address for kernel args because an array of void pointers will point to the first void pointer element. Well, yeah, let's just try and compile it. What I just said, that is to say that this kernel args is a void pointer type. If we got its address, that'd be a void pointer. Oh, I can't even find this function. This is in driver types, which is here, though. Oh, no, it's in CUDA runtime, which is installed. I mean, which is included. Oh, okay. Yeah, no, it does. It finds the function. It's just saying it can't find like a properly overloaded version of it. So Oh, wait. Oh, yeah, I've had this in the whole time. But that's already accounted for with our dim block and our dim grid. Oh, the archetypes it's showing me here, these are the types I am putting in. Not the ones it's taking. Oh, it doesn't need the multiprocessor count. That must be from... So I thought, I was like, oh, this matches because this is what it takes in, but really it's just reflecting what I'm putting in. That makes sense. Yeah, on a normal criminal code, you don't need the multiprocessor count. That must have been something from either that automatic threads for block generator or that multi-device thing. Multi-device launch. Multi-device launch with cooperative groups. All right, built. Built. Run it. Oh, didn't run the kernel. Dang. My kernel. Okay, yeah, we've got 1024 threads per block. So that's the dimension of the block. We have the dimension of the grid. We have an unused parameter. Let's put a comment in why there's an unused parameter. CUDA documentation does not inform how to launch a cooperative group kernel without function arguments. We'll put without any function arguments. We'll put the same comment here. I'll put it on the same line, so because we're at 1080p. I can't imagine those people that used to code with those old style monitors. The little tiny ones. It's black. It's all black and then the pixels only light up green. All monochromatic. I wonder what the resolution was on those. First computer monitor resolution. 640 by 480. Yeah, I mean, that's always the smallest you see for selection. 480p. It's like less than half. Oh. Can't even go down that low on this display. They're above that. Let's just watch one block. And then we won't make any cooperative group calls. See if that works. Okay, it's built. We'll check the time. 11:03, 11:03. Good. Doesn't print. Can like cooperative groups not print? That would be really weird. Plus, I feel like it would have been mentioned in the documentation. Grid group grid. This grid. Maybe we have to call this. No. Well, we did call here, and then we do want to sync it, but the problem is not all threads go in here. So like some threads will be waiting for all the other threads, but they're all asleep, sleeping, slacking on the job. So we could just do this. Do we need to end it? I don't think so. Like, do we need to take away the... no, there's no way. It would just have a destructor that would do anything you needed it to. Create synchronization. They don't actually have like the kernel. I wish they did. I wish they had a kernel example. Okay, so cooperative groups, only devices with compute capability 6.0 or higher. So let's look up what chip setup, what chips those are. Oh, they had an architecture named Tesla. That's weird because they had cards called Tesla. Like there was like the gaming cards, which are GTX. Now they're RTX, and some are GTX. But the ray tracing ones are RTX. Does the 30 series have any non-ray tracing? I don't know. But there's at the time there's just the GTX, which was gaming, and there's Quadro, which was the workstation, and then they had Tesla cards for the data centers. Which would be like, so this is touring like the T1000. Oh, here they are in this column. Oh no, these were Quadros. So it was the T4, Tesla V100, Tesla P40. So Pascal is 6.0. So yeah, that includes even like a GTX 1050, even a GT 1030, and a 1010. I've never even heard of a GT 1010. These all support cooperative groups. Here's Volta. The V100. This is the first data center card with tensor cores in it. And then here's with Volta you have the Jetsons here, because I have a Jetson. And it's on Volta 7.2. Oh, it's one architecture later than the V100 and the V100 and the Titan V. $16 GB frame buffer. Refurbished, so still working. $450. But you need a motherboard that has this SMX2. It's not PCIe. It uses NVLink, which is up way faster than PCIe. And lower latency. Oh, here's a 32 GB version. Buy it now, $425. But you need the motherboard. There's another V100 that does have PCIe. Oh, those are way more expensive. I wonder how much these motherboards cost. Oh, we'll look that up later. Alright, back to the problem at hand. There's no more avoiding it. I have my CUDA check here. So if there was any kind of error, it should be popping out here, and we are running in debug mode. Building it here. Let's Google it, then we can get the samples and look at the source code. I'm kind of slowing down. It's getting late. Let's see here. Cooperative root kernel not running. No error. We'll launch just 128 threads, and then we'll take this stuff off. These off. Even though, like, if you mod it by, if you do modulo 10,000 equals 0, then the first thread should run. But it is not working. Alright, we got the latest executable. And it works. These are super out of order. The warps aren't even in order. I'm surprised they just mix all the letters up with, like, within the print statement. This is crazy. All right. It works now. So how come this wasn't working when we had like a million of these running? Let's try it now. So we'll just run 1,000 blocks, but we'll keep it at 1028 threads per block. Not fucking. Is there like some kind of block number limit? Let's do like 8 blocks. As we saw before, when it wasn't cooperative threads, it was actually working with the 1,024,000 threads. Load. 11:16 p.m., 11:16 p.m. We've got the latest and greatest. Whoa, it's like stuck. Oh, it's waiting to sync between all the threads. So our synchronization is not within this if statement. It's not in the conditional branch, so they should all be able to run. They should all run, yeah. Once it hits here, the thread should go to sleep, and then it should be able to launch all of the remaining ones. Get to here and continue. But it is not doing that. It's all janky. What are we supposed to do? Like, we'll take out these if statements. This is bizarre. So we have our whole grid, and then we just sync it here. Throw it in the sync. My kernel, dim block, dim grid, kernel args. Now let's try that again. Build a little build. $11:19 p.m. Okay, it runs all these. First thread. 8 times 128. That would be 1024. Oh, am I mixing up block and grid here? Grid and block. I am. But shouldn't it still work though? Would just mean 8 threads on 128 blocks. Dim block arcs. Grid block arcs. And then we'll define an order. Same order we call them. That's 8 problem. So I have it on this. Got locked. So we have 367 there. Looks like it's repeating. 359. Oh yeah, they just all run like a super chaotic order now. It's anarchy. Alright, I'll try it, I guess. Oh yeah, that explains why everything was super out of order. It's because our grid was... Our threads per block were really, really small. I guess it didn't have to do with the cooperative kernel. Cooperative group kernel. Now it works, so you can't, you just... So what's the limit here? Is it that you can't have more grids than you have threads in a block? Okay, now let's try, let's go all crazy again. Super, actually first, we'll bring back these modulo operators, conditional branches. Boop, boop. And we can shrink these down. We'll shrink down like what number it has to be divisible by. This only run like 2. This only catch 2 because it's 128. So we'll do if it's divisible by 32. Debug, alright, so we got our executable again, 11:24 p.m. Boop, boop, up, worked. And these are all divisible by 32. We'll try to break it again. If this works. Okay. So this is not working. What if we make this a power of 2? So it'll still be a high number. So our grid dimension, we'll make that a high number. Over 1,000, but it'll be a power of 2. And we'll double check the documentation because that should work. The grid dimension should be able to go very, very high. We'll double check that. It might even be in that device query. Maximum grid dimension. Okay, let's see if it works. Nope, doesn't work. Okay, so it's not that it's not a power of 2. But let's look at our maximum grid. So max dimension size of a grid size for the x direct dimension, it's 2 billion. So it's like the limit of a positive integer before it overflows. A signed integer. Whoa. And maximum size of a thread block is this. Okay, so let's Google, because, yeah, if this doesn't work, I mean, if we don't find anything saying this shouldn't work, then I'll commit this, and I'll get the hash code, and then I'll let my NVIDIA rep know. He's my personal NVIDIA rep. I'm sponsored by NVIDIA. They pay me big bucks to do this. No. He's the, our company has an NVIDIA rep. Maximum. I mean, we just went through the documentation and it didn't mention it. So that's like, this is the official documentation. It's not like there's another section that gets more detailed than this. So just based on the fact that it's not mentioned here, I should be able to report it to the rep, but I'm just gonna look around and Google a little bit because I don't want to pester him. If like, there's just like some possibility I'm not thinking of. I could also try to compile this for like my Jetson Orin or something. Don't care. What is this page? Why did this show up? Oh, okay. Makes sense. How to choose a grid size. Okay, let's just keep shrinking this down until it works. The grid size. Okay, 512 doesn't work. what if we shrink this to our block dimension to 128? Let's try that. We have the reload screen. That means I didn't forget to just CMake. Good little sanity check. Or sanity insurance. Assurance. No, 128 doesn't work. Let's print this out though, actually, just for even better sanity assurance. So we'll do threads. So for these dim3s, it's just a struct of x, y, and z. X, Y, Z. Alright, and then we'll put them next to each other. We'll put it in order. Dim grid, blocks per grid, block dimension, threads per block. Oh, challenge. Eleven 34, 512, 128. Yeah, it's so annoying. It's not even spitting out an error. It's really just the grid size because this is a small number of threads per block. This is like the least you would ever use. 128. That's the least amount of threads per block you got. So block per grid, 512. $256. This better work. Because depending on our network, like we want the number of cores we have. Like each layer in our network, there's weights and biases. So if you add those together, together they're called parameters, or they're a category of parameters. Ideally, we would have each layer will run that through all of our cores. In this case, we have 1,536 cores, and we could have like 8 times that many parameters. That would be an efficient run, like so per layer. So that's only that's like 15,000. total threads we want per block. And this would only be like, this is less than twice as many as that. Well, so it's around twice as many. So we really hope this works. Test this out. No, it doesn't work. We'll do 128. Alright, let's see Mick. Oh, we didn't close the application. By application, I mean program. Oh, works now. Oh, it's not syncing though. But at least it's calling from within the thread. So that's 128 by 128. So that's what, like about 16,000 threads total. I'm not seeing any above. Oh, here's 5,000, 6,000. Can I get an 8,000? Let's print out our total thread number. Total threads. Now let's reduce our data grid to 64. So it's, I mean, we can still do this project, but this is kind of concerning. Yeah, and this is really simple. Like I can just send them this branch. See, I don't have any like obscenities written in here, do I? Let me take out our specific architecture. We don't need separable compilation on either. But we will later though. That's where you can like just compile and link a bunch of different CUDA files together. So if you're only using one CU file, you don't need it. But that would be clean. The error checking. I mean, they'll know what this is doing if they look at this code. So I'll leave this in too. Yeah, 15 lines. Built. It's been C-made. You can say it's been C-made. So, total threads is 8,000. It's stuck again. ISIC here is 6,000. Maybe I should show them the one where it like doesn't even try to start it, or it doesn't print anything. Here, I'll try it without this conditional again. Saying I have to specify the CUDA architectures. That's just the same error over and over. That looks like a bug. And then there was one note about separable compilation, I think of version 11. Separate compilation is no longer required to use grid scoped group. So having it on wouldn't be what breaks it. Okay, so we'll put the CUDA architecture in. We'll add a note here. Running on GTX 1660 Ti. Reload. Build. Bill Nye the Science Guy. Woohoo! Still getting stuck. Turn on all those threads. I wonder. We just highlighted all. Boop. Let's open up a new. Open up a VS Code. We'll check how many threads I went through. 4,100. And there's a total of 8192. Oh, so it printed exactly half of them. Cause so this starts on line 5. 4,100. That would be 4096. I remember the last summer we had it where it didn't work at all. I think that was 512. Okay, that's right. Yeah, that's more concerning to me. I'll report to them the case where it doesn't even run the kernel or say error. Yeah, pretty standard code here. Ooh, will be really nice. We'll see if we can do it for. I think a Python Ubuntu. I wonder what they do over there, or like what operating system they use to compile. I know a lot of people use Linux, but that's what people say they do. A lot of software developers. Everywhere I've been uses Windows for embedded development. So if you're running like FreeRTOS or bare metal, these companies use Windows. But if you're embedded and you're running on Linux, I've only worked at one of those companies. Then we use Linux. Seems like I've read the forums and stuff. Seems like everybody that compiles Linux for an embedded system uses Linux. That's not surprising. I'm sure Linux driver developers do. But for embedded stuff, including driver development, I've only seen Windows. Oh, we didn't close the application down. We got a little ahead of ourselves. VS Code or Visual Studio closed the project. Couldn't take the heat. Okay. Built, run. Here we go. 512 blocks per grid, 128 threads per block. It's not running, and it didn't produce an error. And then 256, it did run, but it got stuck. This is nice too. If I talk to a video, they might tell me how to like not have any arguments. Have a kernel without arguments. Okay, well, 1150. Yeah, not saying anything. And I don't even have these if statements around it. So what if I take away this synchronizer? This is before that though. And I'll take away Cooperative. Thread groups. Cooperative grid. Cooperative group all together. We don't even have to use cooperative groups. Like I said, we could just run a kernel, let it end, synchronize it, and then launch a kernel again. I just don't want to. Alright, let's really get all of our ducks in a row here. Function pointer, casted to void pointer, grid dimension, block dimension, kernel text. I'm gonna change dim grid to grid dim because that's more like how English puts it. Also, it'd be better for autocomplete because the first letters are unique. Oops. Okay, so go here. Function pointer. Oh, you don't have to cast it to void pointer. It does it for you. Yep, function pointer, grid, plot, args. So I'll take this up. Let's see, me red squeeze leaves. Build. Failed. Oh yeah, this isn't a function pointer notation. This is just say it could be any type of pointer. Is there a way to do this where you can just put in, well, any type of like, I don't know what you'd call it, but just like a normal type versus like a function pointer? So I could cast it to int pointer if I wanted. Because when it comes in here, it just comes in as a function pointer. Let's rename this to my kernel. This should build. Yeah, technically I don't have to run CMake if I'm not like changing the files. Oh, I didn't save it. If I'm not changing like the locations of the different files or any type of like compiler settings, I don't have to run CMake again. AIR generator source files. Yay, compiles and run, or compiles. And it runs, but not properly. So this is weird though. Integer. Let's do wayfinder. Okay. You just want to be really really confident. If you're gonna bug a big company, I wonder how well Microsoft treats NVIDIA. Yep, that's it. Okay, so what else do we do? So we'll do our get status, make sure we don't have anything weird in here. We do VS Code folder. This should not be able to be in here. It shouldn't notice this because we have it in our git ignore, anything in the VS Code directory. So let's go to our repo here and we'll see if yeah, it does have VS Code in here. Oh shit. I want to get rid of it. So we'll get RM recursively that folder. Okay, so it's still here, but it's removed. It should be removed from the from our git. Nope. I'll just add these files to this commit. Get rm-r.vs code. Oh, it's saying it has local modifications. Alright, so it's still there, but we've deleted it. Just have to, sometimes you just have to do what the nice terminal says. Alright, git commit message, adding cooperative groups, or we'll say CUDA, adding CUDA cooperative groups for synchronizing a grid. Let's run it again. There is an issue with CUDA. the example kernel is not running nor reporting an error. And we'll push it. Okay. So we're not going to use quadrant groups for a little bit. I will report this to a video. And then, we'll see if they get back to us, how long it'll take. But we must move forward. We must persevere. Okay, but it is officially past my bedtime. So, looking through my notes. Still no Patreon patrons, so no callouts for that tonight. Anything else I wanted to go over? Nope. Looks good. Alright, everybody. Thanks for watching. Please like if you like the stream. Let me know in the comments if you'd like me to have a more regular time. I might not be able to do that. I'm working at a startup right now. But when I do a stream, now's a really good time to hop on. You can just hop on Discord and join the call. Like for now, obviously I can't do that as my channel grows larger and larger. But because there's, I'm a brand new channel and there's not many viewers yet, I have time to answer people's questions, so I can do that. Order preference would be deep learning, CUDA, C++, but I will answer lots of questions if I can. I'm not going to go out of my way and look stuff up, but I already know a lot, so I could probably I can answer like a good chunk of questions. Yeah, and then anyone that signs up for the Discord now, like they'll be able to stay in there until it becomes until it gets linked to Patreon, but that'll be after my channel grows. Anyways, yeah, tonight we didn't get much done, but at least we have some information we can give to NVIDIA, and we still have a path forward on this. So that said, happy coding.